I first taught environmental economics way back when, 25 years ago, in Hamburg, where we had terms of 15 weeks. And the way I did it was 10 weeks of environmental economics and 5 weeks of resource economics. When I taught this stuff at Princeton, we had a 10-week term. Then I came here, we had 12 weeks term, but environmental economics was not taught. It was tied up with climate economics. And then we separated the two. By the time we had separated the two topics, term was down to 11 weeks plus a reading week, right? So that's 10 weeks. And then when I took it over again, sort of during the pandemic actually, always things happened. And those things that happened were illness, strikes, timetabling issues. The implication always was that I had to drop one of the 11 weeks. So long story short, this is actually the first time in 30 years that I'm teaching this particular lecture. So bear with me, right? Really, this is the first time I do much of this material. We're going to do 4 things. We're going to talk about market power and what that does to environmental policy. We're going to talk about tax interactions, and we're going to talk about value chains. Then I think it's going to be a break. We're going to talk about diverse selection and enforcement. And I think that's going to fill 2 hours, but I'm not 100% sure. A lot of this material is a bit tedious. But that's what it is. So I'm going to start with looking at environmental regulation in a perfect market. And I'm going to make things as simple as possible. So we have a demand function where pi, Q is the stuff that you want, pi is the choke price, and P is the price, right? And we assume that this is linear. If this is the demand function, then the inverse demand function looks like this. So that is one side of the economy. The other side of the economy, we have a profit function, capital Pi, which is your revenue. Q is how much you sell, P is how much you charge for this. We have a quadratic cost function, half Q squared. And we have a tax tau on how much we produce. Now, what the company wants to do is maximize its profits. So pi is what you want to maximize, Q is what you decide on, that is how much to put on the market. So the first order condition for maximum profit is the pi dq must equal 0. The pi dq is P times Q plus Q times dp dq. This becomes minus Q and this becomes minus tau. Now we assume that there's no market power. So dp dq is 0, right? That is the definition of no market power. The behavior of a firm does not affect the price. So this thing drops out, and then the solution is, or the supply function is Q is P minus tau. Now we put the economy into a Coulomb equilibrium. So a Coulomb equilibrium, you say we're going to match the quantity on the supply side and the demand side and solve for the price that meets this criterion, right? We also have the Bernard equilibrium, where you're going to price match and then solve for the quantity. What we're going to solve this is Coulomb, right? Let's say this is more common in markets than Bertrand, right? So we have that demand, pi minus Q, must equal supply, P minus tau. which leads to an equilibrium price of pi plus tau over 2. That is, the higher the choke price, the higher the price, the higher the tax, the higher the price. And a quantity, an equilibrium quantity, that is pi minus tau over 2. That is, the higher the choke price, the more you put on the market, but the higher the tax, the less you put on the market, right? Right? This is the simplest representation of a competitive market that you could think of. But I was going to talk about market power, right? So let's now solve the other extreme, the monopolistic market. Demand is still the same, right? Nothing has changed. Demand function is this, inverse demand function is this. Profit hasn't changed. The profit function is as it was. We still want to maximize profits, so the first order condition is in principle still the same. d pi dq, the thing that we're interested in, to the thing that we're decided on, must equal 0. But the big difference now is that dp dq is not 0. In fact, dp dq is minus 1. So the big difference between the price taker, the perfect market, and the monopolistic market is that in the previous slide, this expression here was 0, and now it's minus 1, right? Which implies that the supply function of the monopolist is not p minus tau, but it's p minus tau over 2, right? Which immediately goes to what we think monopolists do. They suppress demand, right? In this case by exactly 50%, so as to increase the price, right? That is what we expect monopolists to do. Stick this thing in a Coulomb equilibrium. The demand side hasn't changed. The supply side is now multiplied by 0.5. And the resulting result is that the equilibrium price is this thing, and the equilibrium quantity is the same as we had before, pi minus tau, but instead of dividing it by 2, we now divide it by 3. Right? So the equilibrium quantity has fallen by, that must be a third, right? Or is it a half? One of the two. Right? So this is where we are. Price taker, equilibrium quantity is pi minus tau over 2. The monopolist, it's pi minus tau over 3. And this obviously is smaller than this. Right? Now things are going to be a little bit more complicated. So, the next question is, what is the optimal tax? Right? For that, we need to define our optimum. The optimum is what the consumer gets, plus what the producer gets, plus what the government gets, minus the environmental damage. This should be a phi. I changed some of the notation this morning, but not all of the notation this morning. So bear with me. We're first going to define the consumer side of things, right? So, consumer pays this, right? Q is how much they buy, P is how much they pay for that, so that is a loss to the consumer. So that's minus PQ. But then they gain the consumer surplus, which is the area under the demand curve. Recall that the demand curve was the choke price minus the actual price. Do I do this right? No, it's the area under the inverse demand curve, right? Yeah. That's P minus, and then you integrate from 0 to how much you actually bought, right? So this is the area under the demand curve. This thing just copies here, right? Now you know why we took a linear demand function. So that the integral is a squared function, right? With minus a half in front. It's minus a half because we have minus x here. And we evaluate that from q to 0. So pq stays where it is. We take this expression here and we stick in the q instead of the x. We take this expression here and stick in the 0 instead of the x. We're integrating from 0 to q, but that's a minus, so this becomes a plus, right? Then this thing nicely drops out against this thing, and we have that the consumer's welfare is this expression here. Choke price times quantity, that's sort of the maximum end of your consumer surplus. This is how much the consumer surplus falls, and this is what we paid for the good, right? So now we know C, so we stick that in here. We knew pi already, profit. Profit is how much you get in revenue minus your costs, minus the taxes that you pay. Now, how much the company gets versus how much the consumer pays, that's a transfer payment, right? So PQ cancels against PQ. This is how much the company pays in taxes, but this is how much the government gets in taxes. So tau Q cancels against tau Q, so that is because it's a transfer payment. And now we see where I messed up the notation, right? Here we had that the externality cost was delta Q, but really in the graph that I'm going to show you in a few slides, it will be a phi Q, right? So here we have the phi Q, and then we turn back to the delta again. Really, guys, I did do this right this morning, but I apparently did not save my slides, right? So a lot of things cancel, and we have pi minus delta times q minus q squared. That is our social welfare function. So what we want to do now is find optimal welfare, right? Optimal social welfare by setting the W, this thing here, to what we choose, and that is our tax that we set, and that must equal 0. Here we're back to the phi. Sorry for the confusion. So this is the welfare function. This is the optimality condition. But what we need to do still is include the response function, right? So dw d tau equals 0. That's the optimality condition for the social planner. But a social planner, of course, should take into account how the market would respond to whatever tax they impose. And that is what we solved a couple of slides ago, that if we assume a perfect market, perfect competition, then this is the equilibrium condition. This is how the equilibrium quantity changes in response to the tax that we impose, right? So we should substitute this expression here to find what is going on here, right? So so we have pi minus phi that remains. What is going on here? This is just pi minus phi. Why do I divide by 2? Okay. I divide by 2 because of this thing, right? So dq, d tau is minus half tau, right? So that is why we have minus 1/2 here. Q squared becomes 2q. So we stick that back in, and then again, dq, d tau is minus half a tau. So we have 2 minus signs here. We multiplied by a 2, that is this one, and then we divide by a 2, that is this one. So again, we have lots of things cancelling. We have minus pi, plus pi, we have phi, we have tau, and really this thing is equal to 0 if the tax is equal to the marginal damages that we do, if tau is phi. So what we've just done is derive that the optimal tax, if there's a single externality and no market power, is equal to the Pigou tax, right? So we're back in, I believe, week 2, right? It's week 9 already, but we're back in week 2. Isn't that great? How much progress we made, right? Now, let's do the same thing, but now with market power. Social welfare function is still the same, but the response function, the equilibrium condition where the market clears, is different, right? Instead of having pi minus tau over 2, we have pi minus tau over 3. So the response function is different. So we stick this expression in here, take the first partial derivative of the thing we care about to the thing that we decide upon. Pi minus phi becomes, we divide by 3 rather than by 2. The 3 is still here, the 2 is here, but no longer cancels, right? Previously we had the 2 here and the 2 here, it nicely cancels, so we still have the 2 minus signs. This thing is here. This must equal 0. Pi no longer cancels against pi, right? We used to have minus pi plus 2 over 2 pi, but now we have minus pi plus 2 over 3 pi, so that no longer cancels. And so that is something that pops up. We also have that phi no longer is equivalent to tau, because we now have 2/3 in front of it. So if we solve this, the optimal tax is 1.5 times the marginal damage. So we're no longer in Pigou, right? But we have to multiply Pigou with a factor. And we also need to subtract half the choke price. So the optimal tax with a monopoly is not the Pigou tax. There is a Pigou-like element in there. The phi is still there, the marginal damage is still there, but it's not the Pigou tax at all. In fact, there's 2 things going on here. This element here corrects for the market power. This is essentially a reflection of the demand response, right? Then this thing here pops up because a monopolist responds differently to a price signal in the form of a tax than a perfect market would. Right? So we have 2 corrections going on to the perfect market. So this is how it looks graphically. Should have made these lines a bit thicker. This is the demand curve, right? That is simple enough. The dashed green curve that you see here is the supply of a price taker if there is no tax, right? If tau is 0. And then the market equilibrium would be Q prime. Market price would be P prime, but that is not indicated. The problem with this solution is that we ignore the externality, right? So what you want to do in a perfect market, you want to tax to the extent that the marginal damage is done. That is, you want to impose a tax tau equal to phi. And then we shift from this particular point to this particular point, right? We reduce total quantity supplied from Q prime to Q asterisk. This really is an asterisk. But the beamer is absolutely hopeless, right? So this is what you do in a perfect market. Now, that is the green curve. Simple as that. The monopolist with zero tax would supply the dashed red curve. That is this curve you see here. And then the optimum amount supplied, or the equilibrium amount supplied, sorry, is the Q double prime that you see here. And that is obviously lower than the supply that you would see without market power, right? So that is one difference. The other difference is that the red supply curve is steeper than the green supply curve, right? That is what drives the fact that you go to a lower supply. Now, if you impose a Pigou tax, that is, you set your tau equal to phi, then you move from the dashed to the dotted red line. That is, you suppress supply even further, and you move, this is the optimum, recall, you move from here to here, you move away from the optimum. So that is not what you want to do. Really what you want to do is first you want to impose a tax of -1/2 times the choke price, that now for some reason has a bar over it. That is, you move from this point to this point, from here to here. This is the correction for market power. And once you have done that, you want to correct back for the externality. And then you end up in this point here, the same point as where you would get with a perfect market with a Pigou tax, right? So that is the things to keep in mind. You want to correct market power, which is a function of the characteristics of your demand function, essentially, because that determines how much market power the monopolist really has. Then you want to move back to correct for the externality. But that is a different horizontal movement because the red curves are steeper than the green curves, right? So to have the same vertical movement, to have the same horizontal movement, you need to apply a different tax, right? So those are the mechanisms that are going on. These are your two starting points. You want to end up here. If you go from the green line to the green line, that is just a matter of applying the Pigou tax. If you want to go from here to here, you need to make two movements. One, you need to correct for market power, and then you need to correct for the externality while taking into account that the curve is steeper, right? So, in a perfect market, the pollution tax is the Pigou tax, is the marginal damage done by pollution, right? Period. Simple, clean, exactly what you want. In a monopoly, if you apply the Pigou tax, output would be too low because the monopolist suppresses demand. So you apply a lower tax, one that also reflects the parameters of the demand function. The environmental tax serves two purposes, correcting both externality and market power. Right? Now we're back to Tinbergen, right? That was lecture 2, if I'm not mistaken. That really what you would want is first take away the monopoly, right? And then apply your Pigou tax. That would be the ideal situation. But if you are not in that situation, that you, for some reason you can't break the monopoly, then your intervention serves two purposes, right? And the environmental tax then reflects that monopolists respond differently to prices than price takers do. Now, this was the simplest case imaginable, right? We had linear functions, we had quadratic functions, and that means that the first order conditions were all nicely linear, and we could solve everything. We assumed monopoly power. Monopolies are actually very rare. Market power is not at all rare, but complete monopolies are actually, you don't see them very much. What I just told you about the difference between a perfect market and a monopoly would carry over to if we assume monopsonies, oligopolies, oligopsonies, Stackelberg, and everything. Anything under the sun you can imagine about market power. I actually don't know whether we actually got our act together and offered industrial organization to you guys. But anything you can imagine about market power, you can work out what would the environmental tax be, the optimal environmental tax. The maths get a lot more complicated, but the insights remain the same, right? If you cannot take away market power, but you can apply an environmental tax, then the optimal environmental regulation is different in perfect and imperfect markets, right? Because there are an infinite number of market imperfections. There is not an infinite number of academic papers about this, but we are approaching infinity. So there's lots and lots of academic work on this. What if we have this market imperfection? What if we have that market imperfection? If you find this exciting, I don't. If you find this exciting, then there is loads and loads and loads and loads of stuff to read. I am not aware of any regulator really using this to redesign environmental policy. There are applications with regard to, and I'll come back to that in a sec, as to where in the value chain you would apply environmental regulation. There's implications of that, but I'm not aware of anybody trying to calculate the Pigou tax and then correcting the Pigou tax for market power outside of academia, right? Inside of academia, there's a million applications. But there is a recent paper by Askar and colleagues. It's a working paper published by the NBER, the National Bureau of Economic Research, soon to be exiled. This is in the US, right? And they look at market power and take a canonical example of market power, and that is the Organization for Petroleum Exporting Countries, better known as OPEC. And what OPEC has done since 1973 is essentially suppress the supply of crude oil in order to drive up the price of oil. And for 2012, for instance, they calculated their suppression of the market was successful. Instead of having 32 billion barrels of oil in a situation without market power, OPEC suppressed supply to 29 billion barrels. That is one thing that OPEC has achieved. The other thing that OPEC has achieved is that because the price is higher, you would actually exploit different sources of oil. And oil is not all equal, and definitely the production of oil is not homogeneous across the world. Because of higher prices of oil, the Congo is profitable, the Alberta tar sands are profitable, and to get oil out of the Arabian desert is actually very simple. You drill a well and it just comes spouting out, right? So that is actually not very energy intensive. But to take oil out of the Congo, you need to work harder. That is, you need to expend more energy to get it out. And if you want to refine the tar sands in Alberta, you actually need to work really, really hard to separate the oil from the sand, right? And that takes a lot of energy. So OPEC not only reduced total demand, total supply of oil, but it also shifted it to dirtier sources of oil. And that, of course, works in the opposite direction, right? This reduces CO2 emissions, this increases CO2 emissions, as well as emissions of a whole lot of other environmental problems that this paper did not look at. So if you put these two effects together, then they reckon that because of OPEC's policies since 1973, the global mean surface air temperature in 2020 would have been, that is 0.03 degrees Celsius higher than in 2020. So OPEC was good a little bit for climate change, right? Sorry, OPEC was bad for climate. It was good for climate change and therefore bad for everybody that does not like climate change. So this is a bad thing, right? No, oh, no. OPEC did a good thing, right? It reduced climate change. Sorry. I'm mixing up my signs again. That is what this paper does. What this paper does not do is look at the effects on technological change. So the first oil crisis was in 73, the second oil crisis was in 78, long before you were born. But as a result of these oil crises in the 70s, people started investing in developing such things as solar panels and wind turbines, right? And those wind turbines, you may think, is something that happened over the last 10 years or so. But really, the research program into building wind turbines started in the late 70s in Denmark, right? And Denmark would never have done this had it not been for the very high oil prices in the 70s. So as a direct consequence of the oil crisis, the oil boycott of OPEC, in the 70s, we now have wind turbines that work, right? I'm old enough to recall the wind turbines of the 70s. They do not work, but the current wind turbines are actually pretty good at what they're supposed to do, right? They do not take this into account. This is another positive effect of OPEC, right? Not to say that OPEC is brilliant or anything. They did lots of bad things as well. But from a climate perspective, OPEC isn't that bad. Okay, second chapter, who to tax. That is, where in the value chain do we apply the tax? And in the previous example, I imposed the tax on production. And that meant that the profit function was revenue minus the cost of production minus the tax that you pay, right? And then we solved the market. But why would you impose the tax on production, right? There's no a priori reason to pose the tax there. You could also pose the tax on sale, right? So then the profit function, this thing disappears, right? But instead, the tax authorities take something out of your retail price. That is what a tax on sale does. So this thing disappears. P here becomes P minus tau, so times Q. Take the brackets away, we move this to the end, and nothing has changed, right? So it does not matter whether you put the tax on production or the tax on the transaction, right? Things haven't changed. Now, we could also tax consumption, right? Then the demand function changes from pi minus p to pi minus p plus tau, right? Because now you pay for consuming stuff. And that implies that the inverse demand function looks like this. The supply function has become simpler. Previously we had p minus tau. Now we have p, right? Because tau is 0 on the supply side. That implies that the market clears at this particular price, and we used to have pi plus tau over 2. Now we have pi minus tau over 2. So the price is different, right? The market clearing. But our demand function is different. Our supply function is different. Supply function is easier, right? If this is the equilibrium price, then this is the equilibrium supply, because Q equals P. So if we put the tax on consumption, then the price is different, but supply, Q prime, is equal to Q triple prime, right? It's pi minus tau over 2. So again, nothing has changed. So it doesn't matter whether we tax production, transaction, or consumption, right? The result is the same. Now, I do this here for a price taker. If you're interested, the same derivations hold if you do this for a monopolist. So, why am I talking about this? Because the market that I assume is actually very simple. What happens if there are two taxes in the economy? And of course, in reality, there are many, many, many taxes, right? So we move from an economy with one tax to an economy with two taxes. We have the environmental tax, tau Q, and we have a profit tax, sigma, right? So now your profit is no longer PQ minus half Q squared, but the taxman takes away sigma of that, right? And what remains is 1 minus sigma of your original profit. That means that the market clears, and the derivation is not all there, but you can read it in the book. The market clears at pi minus tau, because this thing now pops up at the other side of the equation, right? So instead of having tau here, we have tau over 1 minus sigma, sigma divided by 2, right? That is what happens if we tax production, or sale for that matter. I'll get back to that. If we instead tax consumption, and that is equivalent to having this taxing the sale, essentially, so that becomes pi minus tau, 1 minus sigma. So all of a sudden, this 1 minus sigma applies to both the p and the tau, rather than to just the p. And that means that in this case, the market clears at this particular point. Pi minus tau over 2 versus pi minus tau over 1 minus sigma over 2. So what is this? What is the intuition here? A profit tax can be seen as a tax on profits, because that is what it means, but it also can be seen as a subsidy on inputs, right? Because essentially, if you have higher costs, say that your profit tax is 20%, right? If you have higher costs, then your profits fall, and then your taxes also fall. And that means that, and if the profit tax is 20%, then essentially the taxman covers 20% of your additional costs, right? So you could see this as an implicit subsidy on your costs. But you don't get that. You can't deduct your payment in excises from your profit. The taxman would never allow you to do that, right? So this thing is exempt from the profit tax, but this thing is not exempt from the profit tax, right? Now, if the tax is on consumption or on sale, sale is a bit unclear, but if the tax is on consumption, then the price you get in the market falls. That means that your profits are lower, and that means that 20% of that reduction in profit is returned to you because you pay lower taxes, right? So the profit tax treats a tax on consumption asymmetrically differently from a tax on production. And that drives a wedge between between the effect of the Pigou tax, right? And now all of a sudden, if there's two taxes in the economy, it is no longer equivalent to put the tax on production or the tax on consumption, right? The two give a different solution. Of course, if we set sigma to 0, we're back in the original equivalence, right? So it does matter where in the value chain you put your tax if there are other taxes in the economy. Now, so interactions with other taxes, in this case a profit tax, imply that it does matter where in the value chain the Pigou tax is not implied but applied. Now, I took again the simplest model possible. I had a vertically integrated producer and retailer. Reality is much more complicated, right? Typically there is sort of a primary source, and then there's 4 or 5 steps of production and assembly and refinement and all that sort of stuff, and shipping and everything. Typically it takes a lot of companies, a lot of markets before a product reaches you. Depending on how complicated the product is, right? If you take a mobile phone, right, with its thousands of components, there are actually many markets involved and many companies. So then that just makes it a lot more complicated. And definitely if those value chains then starts crossing borders and so on and so forth, you can sort of like see how complicated things can get. And then of course in different parts of the value chain you also have different forms of market power, right? Some markets are almost perfect, some markets are almost monopolies, and other markets are somewhere in between. And that then the first chapter, right? Things are also different with market power. Things are different with taxes interacting with each other. Then things can get very, very, very complicated very quickly, right? So I won't take you there, but the principle is something that you should take away, right? If you have a perfect market, if you have a single tax, then go for Pigou. If you have market power, then you want to correct Pigou for that. If you have other taxes that interact with your environmental tax, then you should think about, do I tax the producer? Do I tax the intermediary? Do I tax the transaction? Do I tax consumption, right? Because then it matters, right? Then it matters. So this is a good time to break. And privileged information is exactly what adverse selection is about, right? That different parties in the market know different things. And in this case, the regulator does not know the costs of emission reduction, doesn't know the abatement costs. The context is one of local pollution. I'm going to assume that there are two types of polluters, one with high costs and one with low costs of emission reduction. And the regulator does not know which polluter is which, but the polluters themselves do know, right? So this is asymmetric information. One participant in the market knows and the other participant in the market does not know. And this, of course, goes back to Akerlof and his Nobel Prize, right? The optimal regulation in this case would be to set a polluter-specific standard or tax, but the regulator lack of knowledge prevents us from doing so. So this is the situation that we're in. Emissions on the horizontal axis, we have prices on the vertical axis. This is the marginal damage curve. Which in this case is actually curved rather than straight, but doesn't really matter. This is the high cost of emission reduction. This is the low cost of emission reduction, H and L. And because it's local pollution, it actually does matter where it comes from. So what you want to do is for the high cost polluter, you want to set this particular tax, RH, and for the low cost polluter, you want to set this particular cost tax, RL, right? But if you don't know which is which, and then you go for the average, you go for somewhere in between, that is the R hat, you would suffer a welfare loss, right? Because essentially for this guy you set the tax too low, and that means that their pollution is too high, goes from this point to this point, and then the welfare loss. You have an environmental loss of this area. You of course have lower emission reduction costs of this area, and then this is your total welfare loss. You also suffer an environmental welfare loss on the other side, because for the low cost polluter you set the tax too low, and that means that they go from here to you want them here and they go to here, right? So you have this welfare change, you have this welfare change, and again you suffer a welfare loss, in this case at the expense of the environment, but to the benefit of the producer, the polluter, right? And so you suffer a welfare loss here, you suffer a welfare loss there. Now, how can you avoid this? What can a regulator do about this? I'm going to consider an emission standard. And what you need is two instruments, right? Because you have two problems. Going back to Tim Bergen, if you have two problems, you need two solutions. And in this case, you have a problem with emissions, but you also have a problem with lack of information, right? So you need an instrument to get companies to reveal their true identity, right? And in this case, that is a subsidy. And you get a subsidy. R hates if you say, I am an expensive polluter, and you get a subsidy RL if you declare I am a low-cost polluter, right? So that is one instrument. You give a subsidy, and you also differentiate the environmental standard, EH versus EL, for companies that say they're high cost versus low cost, right? So you have target differentiation and you give a subsidy. Now, high cost companies should get a less stringent standard or a lower tax, if that is what you're doing. So there is actually no need to reward them for that, right? The reward for declaring that you're high cost is that you get a less stringent target. So companies that are high cost would declare themselves to be high cost, and you don't need to give them a subsidy for that. So our hates can be safely set to 0. They of course may say, I'm a low cost polluter, in which case they do get the subsidy, but they also get a more stringent target, right? So in that case, you need to make sure that your subsidy satisfies this condition, that is the cost to a high cost polluter of getting a high cost target standard should be smaller than still we're trying to incentivize the high cost ones, right? So this is the same cost function, but now for the lower standard, right? So this thing is lower. Yeah, this thing is better than this thing, but this thing would then prevent, the subsidy would then prevent you from going there, right? So if the subsidy is too high, if the subsidy is higher than the sorry, if the subsidy is higher than the cost difference, then everybody would declare to be low cost, right? So the subsidy should not be too high. So that is the first thing. For the low cost firm, it's good in principle to say I'm a high cost one, right? And get a more stringent target. This condition should hold, that the cost difference between accepting a higher standard versus a lower standard should not be such that, or it should not be such that saying I'm a high cost one and therefore I get a more lenient target. The drop in costs should be smaller than the subsidy, right? So for the regulator, this condition must hold, right? So graphically, that works as follows. Marginal damages, but now they're straight lines, just to make things easier. And this is the marginal cost of emission reduction for the high polluter. This is for the low polluter. I put a minus sign in front, so now it's a marginal cost rather than a marginal savings. So the gain from pretending to be high cost if you're low cost is this area here, right? C, D, E, F. So if you're low cost, this would be your target. High cost, you get a more lenient target, so that is a gain. And this is the amount that you would gain in your reduction in costs. this area here, ABFE, is the gain that you would, oh no, it's the loss, sorry, because you get a more stringent target, from pretending to be low cost if you're high cost, right? So the subsidy that you get, that you give, must be somewhere in between these two areas, right? The subsidy must be somewhere in this space. Is that clear? Now, you may think, yeah, you can draw these graphs and you can put up these inequalities. Can we do this in reality? Does this actually work? First, are there legal objections? No, because you can differentiate targets based on objective criteria and relevant criteria. You can't say a company that is led by a woman is treated differently than a company that is led by a man, right? Because that is irrelevant for the environmental pollution that comes out. But you can treat smaller companies differently than bigger companies, or companies in one location differently than companies in another location, if that is relevant for their costs or their pollution or whatever, right? So you can differentiate companies, you can differentiate polluters, also when their difference is actually self-declared, right? That can still be an objective criterion, and you can do that. Conditional grounds are also perfectly fine. There's no legal objection to saying, well, if you meet criteria A to F, you're going to get this subsidy. If you don't meet these criteria, you won't get a subsidy. That, again, is perfectly legal, actually very commonplace. So what you need to do is that a regulator needs to combine these two, a conditional subsidy and target differentiation, so that it induces companies, polluters, to reveal whether they're high cost or low cost polluters, right? And the key finding of the previous two slides was that a regulator should focus subsidies on polluters with low cost emission reduction. Companies or regulators should focus subsidies on low cost emission reduction. The cost of emission reduction are on the horizontal axis. The subsidy is on the vertical axis. The crosses that you see are the actual subsidies given. So where is this graph from, apart from deep in the past when people did not know how to draw graphs, right? Or he knew how to draw graphs, but the software would not allow him to draw a nice graph, right? Let's put it that way. So here in France, we're in the Adour-Garonne water agency. There were contracts with 185 polluters. The contract reveals investment in abatement rather than the costs of abatement, because cost of abatement is actually a very fuzzy concept, but telling the regulator, I'm going to buy this equipment and I'm going to pay 10 million for that, that is of course something that companies know and can easily reveal. And of course investment in abatement, cost of abatement are relatively closely tied, right? Contract also specifies the subsidies given, and some of the subsidies were just the regulator gives them money. Other subsidies were in the form of loans for low interest rates, concessional loans. So we reveal the information, and then they also needed to release or monitor their BOD that they generated and that they discharged. BOD is biological oxygen demand. It is not what you think it is, right? Biological oxygen demand is how much stuff you put into the water. And for reasons only understood by chemists, this is called demand, right? But It is essentially an indicator of, it's an aggregator of how much of certain chemicals you throw into the water that then sort of like stimulate certain plants and algae and everything to grow faster and therefore take oxygen out of the water, right? So this is essentially a measure of how much eutrophying stuff you put into the water and how much oxygen that takes away from the fish, right? That is what biological oxygen demand means. It's a weird term, right? But they should measure that, right? And report that to the regulator. And then in return, they got either a higher tax or a lower tax, right? And as you recall from the graph, the regulator got it right. I was actually astounded when I first read this paper, because it seems sort of like a complicated thing to do, right? But you clearly see that the regulator got the sign right. That is, the greater the cost of emission reduction, the lower the subsidy should be, right? So that worked fine. The dots that you see are what the analyst thought would be the optimal subsidy given. And that should not surprise you. That this follows the theoretical prediction, right? But the regulator actually did not get too far from the optimum, right? Which is to their credit, right? So this can be done. This is not just theory, right? It can be done. So, final chapter, enforcement. So until now, it says here we, but really it's I, have assumed that people obey the law, right? You impose a PGU tax and people pay the tax. And then they change their behavior, right? Or we impose an emission standard and people make sure that their emissions are below the standard. That is what we have done until this point. So let's move away from that. Total costs are now the cost of emission reduction. No, total cost of emissions. The cost of emissions plus the fine that you get if you exceed the standard. And the fine that you get consists of three components. If you're below the standard, if your emissions are lower than what you are allowed to emit, then your fine is 0, right? That is how fines should be. If you don't do anything wrong, you should not get a fine. If your emissions are higher than what you are allowed to emit, then you get a fine that consists of two components. One, a fixed fine for breaking the law, right? And then a variable fine for how much you broke the law, right? How much your emissions exceeded your standard, your target. But there's a third component, and that is the probability pi of getting caught, right? Because oftentimes people get away with breaking the law, right? So those are the components of the fine. So what does that imply for your costs? Here we are. First, the top graph, right? So emissions, we have costs. And the higher your emissions, the lower your costs. So vice versa. If you push down your emissions, you're going to incur a cost of doing so, right? So that is how this curve should be read. Then the fine that you get, that's Fe, is this thing here, right? There is the fixed fine for breaking the law, and then the more you break the law, the higher the fine becomes, right? And then who put that table there, right? Then your total cost function is this thing here, right? That is your total cost function. And obviously your costs are minimized if you are just below your target, right? You want to be just below your target. That is where your costs are minimized. Second case, in the bottom graph, the cost function is the same. The fine function has the same structure, but the total is smaller and the slope is shallower. And as a result, your total cost function looks like this. And then your costs are minimized at this particular point, right? Aidan.
If you were able to reduce low-cost emissions, how would you incentivize companies to reduce high-cost emissions?
Again.
You said that we're supposed to tackle low-cost emissions first, which makes sense, but once we do that...
You're in the previous chapter. Is that right? You're still with the asymmetric information.
Yeah, what we previously talked about. Yeah, you should ask that. But.
You should ask it a while ago. Okay, what is the question?
Once we reduce low-cost emissions, if we're not offering a subsidy to reduce high-cost emissions, how should we do it then?
I'm not sure what the question is.
If we only ever tackle low-cost emissions, we're not going to be able to help reverse climate change. And so how do we incentivize companies to reduce very high-cost emissions like steel, for example?
The objection is to how do we crack this problem and why would we let the high cost polluters off the hook? That is the question.
Or not let them off the hook, right?
Well, to a degree.
Well, how do we get them to not lose so much?
Okay. So the optimal policy, indeed, and this is for local pollution, right? And climate change is not local, it's global. It doesn't matter where the emissions come from. So the argument for treating different people differently is weaker, right? Because this function is flat, right? Rather than, or at least shallow, rather than steep. Indeed, the optimal pollution is for the high cost polluter to allow more, right? To be more lenient in your environmental policy to allow them to emit more. Right? That is the logic of cost-benefit analysis. If it's more expensive to reduce emissions, you should not reduce emissions by so much. So, yes, absolutely, this creates a problem. It creates a problem of fairness and perception, right? You're essentially letting the bad guys off the hook, right? So how would you get them to cut their emissions? Well, you actually do not let them completely off the hook, right? You put pressure on them to reduce emissions. That is the first thing. The way to solve this particular problem is not to look at it in a static framework, as I do here, but to look at it in a dynamic framework, right? So what you need to do is incentivize research and development so that this curve shifts down, right? And that is not something that we've talked about. I mean, I've done basically everything in a static setting and I haven't talked much about dynamics. That is actually going to come next term, right, with Diego. So what you want dynamically is that the costs of emission reduction shift downward. If you have a high cost polluter that cannot move really, that cannot do much about their emissions, you can impose a carbon tax, or you can impose a pigou tax, or you can impose a sulfur tax. if they cannot reduce their emissions, they're just going to pay the tax, right? And you can pay the tax until they shut essentially the factory down, if that is the only abatement option that they have, right? So that is economically very costly. And that is why you would want to be lenient on these guys. So that would be a bad policy statically, right? You're just going to destroy jobs, you're just going to destroy parts of the economy, but not reduce any emissions, right? I mean, if you want me to cut the emissions from getting into work and drive into work, because I live out in the sticks, right, where there's no public transport, well, there's a bus every other week, basically, into town. There is no way I can cut on my emissions from commuting, right? Not realistically. 10 years ago, right? Now, because of technological developments in particularly electric vehicles, I can cut my emissions, right? So the solution here was not to impose a very high price on my commute 10 years ago, but really the solution here was to create the incentives for people to invest in R&D, so that now there is a low carbon, low particulates alternative to my commute, right? Now, how do you stimulate R&D, right? That's actually a very complicated question, because R&D sort of has spillovers, and therefore we have patents and that sort of stuff to sort of give monopoly rights to the generator of R&D so that they can actually recoup their investment. So that is one important component. That has nothing to do with environment, right? That is just R&D in general. The reason that people invest in environmental friendly research is because they believe that in 10 years' time or in 20 years' time, when a product is ready to go to market, there will still be an environmental policy to make it worthwhile to put this product on the market, right? So credibility in environmental policy is everything here. If you indeed promise that environmental taxes are high now and will be higher still in the future, then companies have a very good reason to make their products, to invest in the R&D to make their products more environmentally friendly. If, on the other hand, you promise to make environmental policy more stringent, but then you do not, then companies lose faith in this and stop investing in R&D. So one example is the what is it called? The fuel duty escalator, right? So when you guys were in primary school, the government, and I forget which government it was, announced that every year they would put up the fuel duty on diesel and petrol by, I think, 10 pence per liter, right? And they would do so every year. And they promised to keep doing that indefinitely until everybody drove electric, right? So that is what they promised to do when you guys were in primary school still. And they've done it 1 year, and every year since, the government stood up in Parliament, and it didn't matter whether it was Labour or Conservative, the government stood up in Parliament and said, but this year we're not going to do it, right? So that is a incredible policy, and as a result, nobody believes that the fuel duty escalator will ever come back into force. Similarly, the Canadian government promised something very similar for a carbon tax, that we're going to start with a low carbon tax of, I think, 10 Canadian dollars per ton of CO2. But we promised that next year it's going to be 20, and the year after it's going to be 30, and the year after it's going to be 40, and then 50. And every year since they made that promise, they sort of like stood in Parliament and said, we're not going to do it this year. Next year we're going to keep our promise, but not this year, right? So that is exactly not how you incentivize R&D, right? Whereas the Chinese government sort of says, yes, we're going to cut emissions, and it is keeping companies to this promise. And it's closing factories if you don't meet your standards and so on and so forth. And that is, of course, one is an autocratic government, and sort of like if Xi Jinping says something, we're going to do this in 10 years' time, then we're going to do it in 10 years' time, right, typically. Whereas if you have a democratic government, it's much, much harder to sort of create this dynamic commitment, right? So that is what you want to do, right? You want to create policies that push this curve down rather than just imposing high cost on somebody who cannot change their behavior because they're sort of like trapped in some sort of technology or some sort of location or something, right? Okay, does that answer the question? Okay, and it was indeed on the previous chapter. So I was with this curve, right? So if the fine is high, then your minimum cost is in this point, and you want to cut your emissions to the standard. If the fine is not high enough, then yeah, you increase the cost, but still your optimal behavior, your optimal emissions would be here actually. I think it's more like here. But then again, I'm looking at the curve at an angle, right? Right, so good fine, bad fine, or effective fine, ineffective fine. So let's assume that the fine is effective. Yeah, let's assume that the fine is okay. Let's assume that we want to exceed the standard, right? Then this is our cost function. Trying to get back into my flow, right? This is the cost function. So then what the company does is it minimizes total cost by choosing its emissions. DTCDE must be 0, so that is this function here. This is simply a derivative, right? We don't solve it, we just have a generic cost function. This thing here, this is a fixed fine, doesn't matter. This is also out of your control. So really we have pi fe, and the first partial derivative of that to e is of course pi f, right? So what we have for the company is that the marginal cost of emission reduction must equal the fine times the probability of getting fined, right? That is where the marginal costs of the polluter lie. This would be efficient, that is, we meet the optimal emissions if the marginal costs equal the marginal benefits, right? Marginal costs are pi f, marginal benefits are the P-good tax. So the optimal fine is the marginal damages divided by the probability of getting fined, right? Which implies that your optimal fine is greater than your P-good tax because pi is smaller than 1. If the probability of getting caught is 1, right, then we're back with P-gu, marginal cost equal marginal benefits. If there's only a 50% chance of you getting caught, then the variable part of the fine should be twice the P-gu tax, right? That is essentially what this says. So with imperfect enforcement, what you do is you take the P-gu tax and then you divide it by the probability of catching people doing bad stuff, and that is how you would fine them or tax them, right? This actually has a large empirical literature. This is older stuff. We're in Quebec. We're looking at pulp and paper. Pulp and paper produces lots and lots of chemicals that people just dump in the water. And what we're looking at here is discharges of, again, biological oxygen demand that I explained earlier, and total suspended particles, total suspended substances, it says here. Regressions of that on the production characteristics of 46 plants between 1985 and 1990, all in the province of Quebec. These are the absolutes. This is relative to how much they were allowed to emit. A regressor that is pretty fancy. And the crucial thing here is going on here. This is inspection. And this is inspection in the year before. So we only have monthly data. So, and you don't quite know when the inspection took place. But what you see here is, yes, you are inspected. That year, things fall a little bit, but they're not entirely significant, right? But in the year after, actually things do become significant, and they fall significantly, right? So if you start looking at what companies are doing, if you start looking at what polluters are doing, you actually see a drop in their emissions, right? Which is a good thing. The probability of getting caught doing naughty things increases with inspections. We now move slightly back in time and south of what is still a border, still in the pulp and paper industry. And this is blah, 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 blah. We're spilling chemicals into the water, right? Again, a whole bunch of explanatory variables. This is a dummy, I think. No, can't be a dummy. This is the intensity of monitoring. No effect, right? It doesn't matter whether you're looking at companies. This is the effect of enforcing the regulations. Now what you see is that there's shorter spills of whatever chemicals we're talking about. They fall, and it is highly significant, right? 3 stars means it's significant at 1% or less, right? So enforcement matters, right? These are pretty old examples. This is a fairly recent, well, I recall Eric presenting this as if it were yesterday, but the paper was published 4 years ago by now. Oh God, I'm getting old, guys. So this is monitoring of air pollution. And the EPA, because of resource constraints, only monitors air pollution every 6th day, right? So if you are a chemical facility or an energy facility or something like that, then only once every 6 days you need to report to the EPA how much air pollutants you put into the atmosphere, right? Now Eric copped on and said, well, we actually have satellites looking at air pollution. What is this EPA thing doing that you monitor this every 6th day, right? We actually have continuous measurements of air pollution now because of the satellites that are up there. I forget what this map is about, but I do know what this is about, right? It turns out that what companies do is, so what Eric did was he compared the reporting of air pollution to the EPA, the Environmental Protection Agency, to what the satellite said was the actual air pollution. And on days of monitoring, the two actually aligned perfectly. But then in between, the EPA does not care, right? They don't look at what is going on. And you see that on the other days, the days before the monitoring, the days after the monitoring, emissions were actually higher and significantly higher, right? That is the gray areas that you see here. So monitoring really matters. And EPA, I mean, if you do get caught doing bad stuff, they actually fine you quite substantially, and they may actually shut you down, and you can get into all sorts of legal trouble. So at the days that the EPA was looking, emissions were indeed according to standard. On other days, they were much greater. I think this map sort of shows the exceedances above the standards, which are of course highest in the industrial belt, right? That is what I think the map shows. Final example, another cool example, is from the Bakken. The Bakken is one of the major sources of shale oil, not to be confused with oil shale. Shale oil is much like shale gas, that is, you frack the rock to get the oil or gas that is trapped in small crevices in the rock to get it out, right? That is essentially what fracking is. You just crush the rock and let the liquid or the gaseous stuff come out. If you produce shale oil almost always co-occurs with gas, right? Because essentially they come from the same source. So if you frack for shale oil, you also gonna get shale gas out, right? And that comes out of your pipes. This is typically flared, that is burned on the spot. The reason for this is, yes, gas is a valuable product, but if you produce only a little bit of gas, then the fixed cost of setting up the infrastructure to capture and transport that gas to market is actually too high compared to how much revenue you would get. So gas is a waste product in this case, and you just burn it, right? Because if you let it just escape, it may explode and that sort of stuff. You don't want that. That is why it's flared. Now, across the Bakken, it's a pretty big area in the central United States, frackers self-report the volume flared. The oil and the gas that I showed are monitored, obviously, because this is the product that is going on. North Dakota stands out among other states that cover part of the Bakken in that it limits the amount of gas that can be flared, right? The other states out there say, well, do whatever you want. North Dakota say, no, you can only flare a certain fraction of your gas. The bad thing about flaring is that it turns gas into CO2, right? So this is bad for the climate and also may lead to some other chemicals coming out, but it's mostly CO2 that we're worried about here. Fracker self-report. The regulator actually does not know how much flaring there should be, because the actual ratio of gas to oil varies widely. And they know the average, and they do some samples, but they would not know this from everybody, right? So that is the situation. So we have a regulation in North Dakota. Ruben Lee figured out, again, well, what North Dakota is doing with this self-reporting is a bit silly, because we can actually see flaring from space, right? Because it creates heat. So if you have a an infrared camera, you can actually see this, right? So this is what is going on in North Dakota, right? So before, what was it? This must have been September 2014. You could just do whatever you wanted, right, with your flaring. And this is the difference between reported flaring and measured flaring by infrared from outer space. That's the red curve. The gray area is the confidence interval around it. Now what you see is that there's not a lot of misreporting going on, right? It's not significant. There's a little bit going on. Then this must be June or so, 2014. The regulation was adopted, and it got into force in September of that year. And what you see is that the misreporting increases. That is, as soon as the regulator said you can only flare so much, companies just reported that they were flaring less than what could be seen from space, that what they really were doing, right? So, what do we learn from these 4 examples? What matters is that you actually get punished when you do something bad, right? If we just say, well, you can't do that, then in this case, people tell you that they're doing things differently than they actually do, right? So that is the 4th lesson that you see from this, right? So monitoring matters, changes their behavior, but what really, really matters is enforcement, right? Enforcement is the key. Enforcement was sort of implicit in the Canadian example. It's explicit in the example of the US, and it's really explicit in this particular example from the US again, right? What matters is monitoring, but also if you misreport or if you're caught cheating, then actually there are legal consequences. That's all I wanted to say.